Hello, this is Physics 104A, the homework for Chapter 4. We start with problem number 12. A 148 megagram railroad locomotive can exert 191 kilonewton force. At what rate can it accelerate by itself and when pulling a 14.3 gigagram train? Key to this is being mindful of the units. So let's convert them all to kilograms. The force is 191 times 10 to the third newtons. And in part A, we have a mass of 148, it says megagrams. So that's times 10 to the 6 grams. Let's get that in kilograms, so everything is in MKS units. So that should be 148 times 10 to the third kilograms. Then we can do acceleration equals force divided by mass. And you can see I've divided them there, and I get 1.29 meters per second squared. Now then we're going to add on something, a car that is much more massive than just the locomotive itself. It's measured in gigagrams. So the mass is going to be 148 times 10 to the third kilograms plus 14.3 gigagrams. We need to get all that in kilograms. So that becomes 14.3 times 10 to the 6 kilograms. When we add those together, the mass is 1.4448 times 10 to the 7th kilograms. Then acceleration is force divided by mass, and you get 1.32 times 10 to the negative 2 meters per second squared. Number 15, a motor protein. It exerts a 6 piconewton force. What acceleration will give a molecular complex with mass 3 times 10 to the negative 18 kilograms? So again, just like the previous problem, this is very much a matter of properly doing unit conversions. We want to, just as with the locomotive problem, get it all in MKS units. So the force, 6 piconewtons, is 6 times 10 to the negative 12 newtons. The mass is already in kilograms, 3 times 10 to the negative 18. Acceleration is force divided by mass. And we get 2 times 10 to the 6th meters per second squared. Number 16, starting from rest, constant acceleration, a 940 kilogram racing car covers 400 meters in 4.95 seconds. Find the force on the car. Well, before we find the force, we need to find the acceleration. We use kinematics for that. Here I've listed out the given information. We can use this kinematic equation that delta x is v naught t, which is 0 because it starts from rest, plus 1/2 at squared. So acceleration is 2 times displacement over t squared. We plug those numbers in, we get 32.6497 meters per second squared. Then multiply that acceleration by the mass, and we get a force of 30.7 kilonewtons. Number 17, an egg dropping contest. An 85-gram egg in a large styrofoam block. The force on the egg cannot exceed 28 newtons. And if the block hits the ground at 12 meters per second, by how much must the styrofoam compress on impact? All right, so here we have the mass of the egg. The force, the maximum force is 28 newtons, and we're going to need some kinematics to figure out the distance that it can fall, the maximum distance. But here's the information as it's given. We're going to use F equals ma to find the maximum acceleration. Then we'll use the kinematic. So acceleration is maximum force divided by mass. And so it's 329.4118 meters per second squared. And it's negative because it's going to be decelerating. Now, let's use the kinematic equation. V squared equals V naught squared plus 2a delta x. So delta x is, we have a final speed of 0 minus V naught squared over 2A, and we end up getting 0.22 meters or 22 centimeters. Number 20. Your spaceship crashes on one of the sun's planets. Fortunately, the ship's scales are intact and show that your weight is 532 newtons. If your mass is 60 kilograms, where are you? And we're going to need to consult Appendix E, or some information about the strength of gravity on different planets. So we get that weight is mass times g. And we want to find the g, the acceleration due to gravity on different planets. On Earth, we know it's 9.80 newtons per kilogram, but we're on different planets here. So your weight divided by your mass, 532 newtons over 60 kilograms, and we get 8.87 newtons per kilogram. You can look up in the table in Appendix E at the different planets, and both Venus and Uranus, their surface gravities are both 8.87 meters per second squared. So it could be either of those planets. Number 21, your friend can barely lift a 35 kilogram concrete block on Earth. How massive a block could she lift on the moon? So to be able to lift 35 kilograms on the Earth, we want to think about the weight that is. So the force that you can apply, I've drawn a force diagram, the lifting force up and the weight down. The force that this person can apply in lifting is 35 kilograms times 9.8 newtons per kilogram. So this person can exert 343 newtons of force. Now on the moon, we have that same force. We're now making equivalent to the weight of the concrete block, or of another block on the moon, and that equals the mass of the new object times g of the moon. So the mass of the object is going to be the force that the person can lift with, divided by g on the moon, 343 newtons divided by 1.62 newtons per kilogram, and this person can on the moon lift a 212 kilogram object. And notice that that's 6 times what the person can lift, 6 times the mass of what the person could lift on Earth. Number 25. A 50 kilogram parachutist descends at a steady 40 kilometers per hour. What force does air exert on the parachute? We draw a force diagram. Force of the air going up, the weight of the parachutist going down. The sum of the forces is mass times acceleration. It says a constant speed. It actually says a steady 40 kilometers per hour, but actually the speed is irrelevant. All that matters is the acceleration, which is 0. So we have the force of the air, which is upward, so it's positive, minus the downward weight, m times g equals 0. So we solve for force of the air equals the weight of the parachutist, 50 kilograms times 9.8, and we get 490 newtons. Number 26. A 930 kilogram motorboat accelerates away from a dock at 2.3 meters per second squared. Its propeller provides a 3.9 kilonewton thrust force. What drag force does the water exert on the boat? You can see my force diagram. The boat is going to the right. So the thrust, this is the force of the thrust pushing to the right. The drag is pushing back to the left. We have the given information. We want to know the force of the drag. Let's use our force diagram to apply F equals ma. So the force of the thrust minus force of the drag equals ma. And we just solve for force of the drag. Here I've plugged in all the values, and solving for force of the drag, it's 3,900 newtons minus 2,139 newtons. And so we get the force of the drag is 1,800 newtons. Number 33, very simple spring question. What force is necessary to stretch a spring 48 centimeters if its spring constant is 270 newtons per meter? Well, the force is the spring constant times the displacement. So 270 newtons per meter. We need the displacement in meters. And so we'll say 0.48 meters, and we get 130 newtons. Number 35, a spring with spring constant 340 newtons per meter is used to weigh a 6.7 kilogram fish. How far does the spring extend? We look at the force diagram. The spring is pulling upward on the fish with a force of kx. The weight of the fish is pulling down on it, mg. We're going to apply F equals ma, so kx minus mg equals 0. And we're going to solve for x. So x is mg over k. Here I've plugged in all the values, and we get x is 0.193 meters, or 19 centimeters. Number 36. A 2280 kilogram car accelerates from rest to 31.2 meters per second in 9.48 seconds, moving in a straight line with constant acceleration. Find the net force acting on the car. If the car then rounds a bend 166 meters in radius, what net force acts on it? So for part A, we use kinematics. We need the acceleration if we're going to find the force. So this is the appropriate equation. V equals V naught plus AT. We're going to solve for A. A is V minus V naught over T. Of course, V naught is 0. And we get an acceleration of 3.29 meters per second squared. Once we know that acceleration, we multiply it by mass of the car to get the force, 7,500 newtons. Now for part B, it's going in a circle. And so we're going to take the speed that it was going, 31.2 meters per second, and find the force to bring something around in a circle, that radial or the centripetal force. Force is ma, which is mv squared over r. So we have the mass, we have the speed that was given in the original information in the problem, 31.2 meters per second. We're going to divide by the radius of the bend in the street, 166 meters, so we get 13.4 kilonewtons. Number 40. A 975 kilogram elevator accelerates upward at 0.754 meters per second squared. Pulled by a cable of negligible mass, find the tension force in the cable. Very important, as with all these force problems, that we start by drawing a force diagram. Tension upward, weight downward. So then we can apply F equals ma. Tension minus mg equals mass times acceleration. We want to solve for the tension, so tension equals mg plus ma. We can factor out m, so it's m times g plus a. And it is important to note that it says it's an upward acceleration. If it were downward, that would be minus 0.754 meters per second squared, but this is upward, so it's plus. And in the end, we get a tension of 10,300 newtons. Number 41. Same setup as the previous problem. Now it says the tension in the cable is 8.85 kilonewtons. What are the magnitude and direction of the elevator's acceleration? So I wrote, see the force diagram for the previous problem. There it is at the bottom of the screen. We're going to start with T minus mg equals ma, just as we did before, but now we're going to solve for acceleration. Acceleration is T minus mg divided by m. We plug in all the values, and we get acceleration is negative 0.723 meters per second squared. So because the tension in the cable was less than the weight of the elevator, this thing is going to accelerate downward. That gives the negative acceleration. So it's an acceleration of 0.723 meters per second squared, and it's downward. Number 46. A 74 kilogram tree surgeon rides a cherry picker lift to reach the upper branches of a tree. What force does the lift exert on the surgeon when it's at rest, moving upward at a steady 2.4 meters per second, moving downward at a steady 2.4 meters per second, accelerating upward at 1.7 meters per second squared, and accelerating downward at 1.7 meters per second squared. We want to find the force. So the object of my force diagram is the tree surgeon, the person himself. We start with drawing the force diagram. As you can see there, F equals ma becomes F minus mg equals ma. We want to solve for the force, so we get ma plus mg, or factor out the m and get m times a plus g. Now, parts A, B, and C all have the same answer because they all have zero acceleration. And so when we plug into this formula for an acceleration of 0, the force is just actually the weight of the person, 725 newtons. I'm going to round that with two significant figures to 730 newtons. Now in part D, we've got an upward acceleration. So we'll make acceleration be plus 1.7, and we get 850 newtons. For part E, it's a downward acceleration. So the cherry picker, the floor of it that the person is standing on, exerts a force of only 600 newtons. Number 63, a comparison of abilities of two aircraft. With its fuel tanks half full, an F-35A jet fighter has a mass of 18 megagrams and engine thrust of 191 kilonewtons. An Airbus A380 has a mass of 560 megagrams and a total engine thrust of 1.5 meganewtons. Could either aircraft climb vertically with no lift from its wings? If so, what vertical acceleration could it achieve? Well, for an airplane climbing vertically, we've got the thrust that's pushing it straight up, the weight of the plane pulling down on it. And to climb vertically, we're looking for a situation where the force, the sum of the forces, has to be greater than 0. Basically, the thrust has to be more than the weight. So let's look at the fighter plane. I have its mass, the thrust, and we'll do the sum of the forces is tension minus mg, which is 14,600 newtons. And since that's positive, it can climb vertically. Now, if I had done in the line where my marker is F equals ma, that would be T minus mg equals ma, then we could solve for the acceleration. But I've just taken the sum of the forces, and now I'm setting that equal to ma. To solve for acceleration, you do the sum of the forces divided by the mass, and you get 0.81 meters per second squared. So this plane is capable of accelerating upward, straight up at 0.81 meters per second squared. We can do the same with the Airbus jetliner, and you can see the numbers that I've plugged in. The sum of the forces, thrust minus weight, is negative 4.0 times 10 to the 6 newtons, which means it cannot climb vertically because the weight of the plane is greater than the thrust that its engines can provide. Number 73 has two masses joined by a massless string. A 30 Newton force applied vertically to the upper mass gives the system a constant upward acceleration of 3.2 meters per second squared. If the string tension is 18 newtons, what are the two masses? Here's my force diagram. Since we're dealing with multiple objects, let's do two separate force diagrams. To the right is just my picture of the masses, and I'll call the one on top mass 1 and the one down below mass 2. Look at the force diagram on the object number 1. We have the pull upward, and downward we've got its weight, m1 times g, and the tension in the rope. Now we do a force diagram for object 2. There's the tension in the rope pulling up, and downward is m2g. I want you to notice that the pull that we're applying is not being directly applied to object 2. That's only applied to object 1. Let's do F equals ma. For the top mass, we can say the sum of the forces is m times A. And we have to keep in mind what we're trying to solve for. What are the two masses? All right, so let's see if we can solve for mass 1. We go into F equals ma and we do the pull upward minus tension minus m1g equals m1a. And we want to get m1 by itself, so let's get all the m1 terms to the right. So p minus t equals m1 times g plus a. Solving for m1, we get p minus t over g plus a. We can plug in all those values. 30 Newton pull minus 18 Newton tension divided by g, which is 9.8, plus the acceleration upward 3.2, and we get a mass of 0.92 kilograms. Now, for the bottom mass, let's also do F equals ma. The tension upward minus m2g is m2a, so the tension is m2 times g plus a. We'll solve for m2, that's t over g plus a, plug in those values, and we get 1.38 kilograms, which I can round to 1.4 kilograms. Now, to check our solution, let's consider the whole system as one unit, and just forget that there are two masses with a string in between them, a massless string. Let's just consider them to be one unit, and a 30 Newton force is applied to it. So in that case, here is my pull upward, the whole system, and its weight, capital Mg, which is m1 plus m2. So then we have P minus mg equals ma. We can solve for the mass, and what we get is 2.3 kilograms. So the masses should add up to 2.3 kilograms. That's how we can check our work. And that is the end of the Chapter 4 homework. Have a great day.